questions 21 through 25 on the 2007 Grade 7 Gauss Math Contest. In the diagram, how many paths can be taken to spell Carl? Well, let's see. The first path, of course, is right down the left side. So that's like this. Then we're okay until we get to here, and then we'll do that right there. So that's sort of like this, C-A-R and then L. Okay? Then we've exhausted the possibilities for that guy, correct? So we turn our attention to the next scenario. And that is K-A, but then now this guy right here. And for that one, there's two ways. You can go to L here and L there. So if I write those out, it will be like K-A and then R, L here, and then K-A-R, L there. Okay? So we're done with this first A right there. And the second A, it's pretty much the same story. There's that scenario, which is K-A-R-L. Then there's K-A-R until there, and then that L. So that's K-A-R, but then the other L. Now we're done with that guy, so now we have to go here. And that one, there's this L and that L. So there's two ways of doing that. So that's going to be K-A-R-L, K-A-R, the other L. So you just have to fiddle around with this diagram, and if you do, you get 8 possible choices, and therefore number 21, the answer is D. The average of 4 different positive whole numbers is 4. If the difference between the largest and the smallest of these numbers is as large as possible, what is the average of the other two numbers? I'll let my numbers be A, B, C, and D, and they tell me that the average is 4. So that means I have to divide by 4 to get 4. If I cross multiply, I get A plus B plus C plus D is equal to 16, correct? So now we have to make a little bit of a table and see what possible scenario will work for us. I want the difference between the largest and the smallest to be as large as possible. I'll let this A be the smallest, and I'll let D be the largest. Okay? So, let's say the smallest possible number I can have is 1, because they're saying that they're all positive whole numbers. And the largest possible is going to be 16. But if D is 16, then D plus A will be 17, and that's not going to work, right? So let's make D 15. That way, this at least can work. 1 plus 16, or 1 plus 15 rather, is 16. But B and C would have to be zeros for that to work, and that's not going to fulfill the criteria of the question, because they're 4 different positive whole numbers. So this doesn't work. Okay, no problem. Keep going. Let's try 114. Well, it's 114, then this sum of B and C has to be 1. And the only way to do that is 0 and 1. But both of these numbers have to be positive, right? So that can't work. Okay, let's try 13. That means B and C have to add up to equal 2, correct? And the only way to do that without having a 0 is 1 and 1. But that doesn't work because all 4 are different. Okay, let's keep going. How about 1 and 12? Is that going to help me? Sooner or later, we're going to get something that works. 1 and 12, well, that means B and C have to add up to be 3. And the only way to do that without a 0 is 1 and 2. Well, again, we don't have 4 different numbers. Let's try 1 and 11. That means B and C would have to add up to be 4. And the only way to do that without zeros is 1 and 3 or 2 and 2. And neither of those scenarios give me 4 different numbers. Okay, how about 1 and 10? That means B and C have to add up to 5, and that can happen with 2 and 3. and this satisfies the question. So now they're asking for the average of the other two. The other two numbers are 2 and 3. Their sum is going to be 2 plus 3 and divide by 2 to get the average, and that is 5 over 2. So number 22, the answer is B. A square is divided as shown. What fraction of the area of the square is shaded? Let's blow this up. All right. So these symbols mean that those sides are all the same. So let's just say this is 1 and this is 1. Okay, so that means this square has a side length of 2. It's perfectly fine to do that. So the total area of the square is 2 times 2, which is 4. Now we have to figure out the area of the shaded region. So how do I do that? Well, I'm going to draw a triangle like this. That red triangle, I'll just call it red triangle, make it easy for you. That is going to help me, because if I take that red triangle and I subtract from it this small triangle, I'll call that small triangle, I don't know, S for small. This guy right here, this tiny little triangle in here. If I do that, that will give me the area of my shaded region. Correct? So I think we can do that. Shouldn't be a problem. The red triangle is 1/2 base times height. The base is from here to here, which is 2. And the height is from here to here. And that height is 1. It's the same as that one downstairs. So there we go. We got the area of that red triangle. The small triangle, which I labeled S, again 1/2 base times height. The base is from here to here, which is 1. And the height is from here to here. And because of the symmetry of this diagram, that essentially is 1/2. It's from here to here. So there we go. So therefore, the area of the shaded region is going to be 1 minus 1/4, and that is equal to 3/4. So now what they want in the final part of this question is the fraction that the shaded region represents of the total square. So that means the fraction would be the shaded region divided by the area of the total square, divided by t. So AS is 3 over 4. T we had earlier figured out was 4. So 3 over 4, invert and multiply. And that gives me 3 over 16. So 3 over 16 is the answer to this question. And that looks like choice C. In the multiplication shown, P, Q, and R are all different digits, so that PPQ times Q is equal to RQ 5Q. What is the value of P plus Q plus R? So this will involve a little bit of experimentation, right? So let's go and see what we get. All right, so the first thing I notice is that when I write this out, that Q times Q has got to equal Q, right? This times this has to equal Q. Not necessarily, but at least that's where I'm going to start. Okay, well, Q times Q equals Q. The only way that's possible is if Q equals 1. But if Q equals 1, then we'll have PP1 times 1 is equal to RQ 5Q, and that doesn't make any sense, right? Because PP1 times 1 is just PP1. There's no way you're going to get a 4-digit number. So what that means is that Q is not 1. All right, no problem. Let's keep going. Let's go back and think about this. Q times Q has to give me Q. Well, it could be, for example, 5, right? Because if you have 5 times 5, it equals 25. So at least I got that 5 there. And then I'm most likely going to carry the 2, right? Just like how you did way back when you first learned multiplication. So let's let Q equal 5. Let's see what we get. That would mean it'd be PP5 times 5 is equal to R5, 5, and 5, right? Because Q is 5. Let's see if this works, if we can get integer values for P and R, right? Because these are digits, they have to be integers. All right, let's see. 5 times 5 is 25. So if that's the case, we have P5 times 5, 25. So 5 carry the 2. 5P and then plus 2. So 5P plus 2 has to go in here. And that represents this 5. Correct? So that means that 5P plus 2 has to be equal to 5. So that means 5P is equal to 3. So P is equal to 3 over 5. Well, obviously that doesn't work, right? There's no way that we can have P is equal to 3 over 5. P has to be an integer. Okay. Well, let's move on. But one thing I did notice is that 5P plus 2 doesn't necessarily have to be 5, right? It could be something that ends in 5, because this we have written as 55. So it could eventually be made into 55 by adding something else. So how about if 5P plus 2 was 15? Let's see, do we get an integer value for P? 5P would therefore be 13, and unfortunately we don't get an integer for P. How about if 5P was 25? Similarly, 5P plus 2, I mean. Similarly, 5P will be 23. Again, you don't get an integer value. And if you keep doing this, you'll notice that this scenario just doesn't work anymore. All right, no problem. Let's try Q equal to something else. What else can I use for Q to make Q times Q have a Q? Well, how about 6, right? 6, that would be P6, 6, and then this is going to be R6, 5, 6. Let's see if we get integer values. Okay, so 6 times 6 is 36, so that basically means that the 6 goes here and you carry the 3. 6 times P is 6P plus 3, so 6P plus 3 is basically going to give me this 5. Okay, so 6P plus 3 has to be 5 or something that ends in 5, right? So this one gives me 6P is equal to 2. Well, that doesn't give me any integer solutions. No problem. How about 6P plus 3 is equal to 15? Remember, it can end in 5. This gives me 6P is equal to 12. So that means P is equal to 2. Okay, let's see if P equals to 2 works. That means it's 226 times 6. And 226 times 6 is 1356. Unfortunately, that doesn't match this format, right? Because that's 6 and that's 3. Okay, no problem. P is not 2. Let's keep going. I'm pretty confident that Q is 6 though. Let's keep going with this strategy. 6P plus 3, it's not 15, but let's say is it 25. That would mean 6P is equal to 22. Well, P is not an integer. Let's keep going. If 6P plus 3 is equal to 35, that would mean 6P is equal to 32, and that doesn't give me an integer. How about if 6P plus 3 is equal to 45? That would mean 6P is equal to 42, and therefore P is equal to 7. Okay, P is equal to 7. Feeling good about this one here. So that would mean my equation becomes 7, Q is 6 times 6. And let's see, 776 times 6 is 4656. Is it in this format? Yes, it is. So therefore, R is 4, Q is 6, and P is... So they wanted me to figure out in the question P plus Q plus R. So that's going to be P was 7. So 7 plus 6 plus 4, and that is 17. So number 24, the answer is E. The Canadian Mathematics Competition reception desk has a tray in which to stack letters as they arrive, starting at 12. The following process repeats every 5 minutes. Step 1. 3 letters arrive at the reception desk and are stacked on top of the letters already in the stack. The first of the 3 is placed on the stack first, and the second letter next, and the third letter on top. Step 2. The top 2 letters in the stack are removed. This process repeats until 36 letters have arrived and the top 2 letters have been immediately removed. Once all 36 letters have arrived and the top 2 letters have been immediately removed, no more letters arrive, and the top 2 letters in the stack continue to be removed every 5 minutes until all 36 letters have been removed. At what time was the 13th letter to arrive removed? So we have to make a little bit of a list, a table. So I'm going to start at 12 noon, and every 5 minutes after that, I am going to obviously add some papers. So we got 12, 12:05, 12:10, 12:15, and so on. So here we go. Let's start filling in this table. At 12, the first 3 papers arrive, so I'll just label them 1, 2, and 3. And then after they arrive, they remove the top 2, correct? So when they remove the top 2, I'll just circle those. And then we get to the next time period, which is 12:05. When that time period starts, the only thing that's left in the stack is the paper that I have labeled 1, because papers that were labeled 2 and 3 were removed. Now we add the next 3, and I'll call those 4, 5, and 6. Okay? Now we get to the next 5-minute period. And when you do, it starts with just 1 and 4. Why? Because 6 and 5 were removed. And this process continues. So I'll just do a few more, and then I'll fill in the rest, because you'll get the idea by then. Now at this point, at the 10-minute point, we add the next 3, which are 7, 8, and 9. And then when we get to 15, 2 of those have been removed. So we start off with just 1, 4, and 7. The pages that are labeled 1, 4, and 7. The first one, the fourth one, and the 7th one. Now at 15 minutes, you add the next 3, which are 10, 11, and 12. And then you move to the next time period. But before you do, you have to remove 2. So you start this next time period with the pages that are labeled 1, 4, 7, and 10. Now you add the next 3, which would be 13, 14, and 15. But then you immediately remove 2 of them. And then you start the next time period with 1, 4, 7, 10, 13. You add the next 3, which are 16, 17, and 18. But then you immediately remove the top 2. And you start the next time period with 1, 4, 7, 10, 13, 16. And you add the next 3, which would be 19, 20, 21. And then you immediately remove the top 2. Then you start the next with 1, 4, 7, 10, 13, 16, 19. You add the next 3, which would be 22, 23, 24. And you immediately remove the top 2. And you start the next time period with 1, 4, 7, 10, 13, 16, 19, and 22. Correct? And then, of course, you add the next 3, which are 25, 26, 27, and you go on from there. So at this point, I think you get the hang of it. I think you can do the last few. I'll just fill them in. So I filled it in until all 36 have been added. Now, what I want to do is, now that all 36 have been added, we have to now start talking about what's going to happen next. No more new papers are coming in. Now it's just going to be a clearinghouse. We're just getting rid of them 2 at a time. So I will shift this over and extend this table, and let's see what we get. So at the 55-minute mark, that is when we placed the last of the letters, which were 34, 35, 36, correct? And immediately we removed the top 2. So when we get to the 60-minute mark, these are the only letters that are remaining. And there's 12 of them. So there's 12 letters remaining. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then each of these intervals, you're going to remove 2 until there's none left. So they want you to figure out, when was this guy removed? The 13th letter. Okay, let's see. So in this interval right here, the 60-minute mark, you remove 34 and 31. And if you do, what's left are these guys, 19, 22, 25, 28. At the 65-minute time of this question, we remove the next 2, which are 25 and 28. So now you're left with these guys. Then at 70 minutes, you remove the next 2, which would be the 22nd and the 19th. So you're left with these guys. And then at the 75th minute, you remove the 16th and the 13th letter. And that is what they're asking. At what time was the 13th letter removed? It was removed at 75 minutes from the start, which was 12. 75 minutes from 12 is 1:15. So therefore, number 25, the answer is 8.